Welcome back, everybody. In this video, we're going to continue with section 4.4 by talking about permutations and combinations. So we worked on the fundamental counting principle, which told us about how you could break down a big task into subtasks to figure out the number of ways of completing a big task. And then we also talked about how n factorial tells you the number of ways of arranging all n of something, like the number of stores you have to visit on your route or the number of books on a bookshelf were a couple of examples we had used. For permutations and combinations, it's kind of a similar idea to that, only instead of arranging all of something, we're arranging a subset, that is, some of the items. So here's the definition or description from the book. So these are kind of long, so we'll read through these carefully. There's permutations and combinations. We're going to read permutations first. Permutations of items are arrangements in which different sequences of the same items are counted separately. For example, with the letters A, B, and C, the arrangements A, B, C, A, C, B, and so on are all counted separately as 6 different permutations. In short, the order that those 3 letters are in makes a difference. Combinations of items are arrangements in which different sequences of the same items are not counted separately. For example, with the same 3 letters, these arrangements ABC, ACB, and so forth would be considered the same combination. So the big difference between permutations and combinations is that for permutations, the order matters. For combinations, the order does not matter. But in each case, we're still taking a selection of some items and counting the number of ways of ordering those selections. Okay, in short, out of n total things, books or cars or people or whatever they are, out of n total things, we're going to pick r of them. So n and r are variables. N is the total number of things. R is the number of things being selected. We want to know how many ways are there to select those r items out of the n total items. And so a big fundamental question you ask yourself is, does the order of the selected items matter? If the order matters, it's permutations. If the order of the selected items doesn't matter, it's combinations. Okay, some examples. We're not calculating here. All we need to decide is it permutations or combinations? Okay, suppose that you have 5 friends and you want to invite 3 people over for dinner. You don't want to invite all 5 because you don't want to have a huge party, but you want to have a few people over. So you're going to invite 3 people. So the question is, out of those 5 people, you got to choose 3. Does the order that you select the 3 people make any difference? And the answer there is no, because people are either in your house or they're not. Okay, so they're either selected or not selected. So that makes it combinations. Order doesn't matter. Okay, 5 people run in a race. The first place person wins $1,000, the second person gets $250, and the third person gets $50. 4th and 5th place get nothing. Okay, the order that the 5 people are in, does it make any difference? Yes, of course it does. You definitely want to be in the top 3, otherwise you win nothing. And also being first or second matters because first place person gets $1,000 and second place only gets $250. So here, those top 3 winners, choosing those 3 winners matters. And so it is permutations because order matters. Okay. For part 3, suppose we have the same race, but instead the top 3 people will each get $400 and then the 4th and 5th place people get nothing. So does it matter in this case whether you're first or third? It doesn't matter, right? Either way, you're going to win $400. And so this one, it's combinations, the number of ways of choosing the 3 winners out of the 5 people. That's just combinations because the ordering of those 3 winners doesn't make any difference. All right, so we want to work on coming up with formulas for how we can calculate permutations and combinations, and we'll treat permutations first. So as before, n is going to be the total number of items there are, and r is the number of items that are selected. And there's a rule for this, a formula. When n different items are available and r of them are selected without replacement, this is all without replacement, the number of permutations, that is where order matters, is given by this formula. It's n factorial divided by n minus r factorial. And there's a couple of different notations for this. You may see a NPR symbol. That's the one that our book tends to use, is NPR. Some calculators, other books, Google will use this. It looks more like a function from algebra to put the P in front and then NR. So one thing to be careful of right now is before we were using P for probability. In this part of this section, P is standing for permutations. Okay, so be careful about that. Our book is going to use a capital P for this rather than a little p, just so you know. And so PNR stands for the number of permutations of n things taken r at a time. How many ways are there for you to choose those r things out of n and have the order matter? And how you calculate it is it's n factorial, the number of ways of arranging all the items, divided by n minus r factorial, which is the number of ways of arranging basically the non-selected items. So we want to see how this formula comes about. So let's say that we have the 5 letters A, B, C, D, and E. And we want to know how many ways are there to choose 3 letters from that group. A, B, and C, C, D, and E, B, D, and E. How many ways are there for us to choose those letters? Okay, first of all, there are 5 factorial or 120 ways to arrange all 5 letters. So I've started listing them here, A, B, C, D, and E, and then I switched the E and the D, A, B, C, E, D, A, B, D, E, C, A, B, D, C, E. So if we had all day, we could sit and write down all 120 different arrangements of these 5 letters. We know that there's 5 factorial or 120 ways of arranging all 5 of those letters. Okay, so the n factorial in the formula comes from that, like here, that 120, the 5 factorial, the number of ways of arranging all those items. But here in this problem, we're only choosing 3 letters from the 5. So the first group here, ABC, we would count that as one possibility because it doesn't matter what order the D and E, the non-selected items, are in. ABDCE and ABDCE, again, we would count those the same. So here, what's going to happen is that 120, that 5 factorial, 120, we're going to end up dividing by 2. Or more properly, 2 factorial, which is the number of ways of arranging the non-selected items. Look at it this way. Suppose that we have a race with 5 people in it, and we're going to give different prizes to the top 3 people, okay? And the 4th and 5th people don't get anything, okay? So the order that the top 3 are in matters. The order that the losers are in, the 2 people who lost, it doesn't make a difference. So we're going to divide by the number of ways of arranging those last 2 people. And that's where that division in here comes in. And it's n minus r. If r things are selected, n minus r is not selected. Okay, so the comment here at the bottom, if we're choosing r of the letters, then n minus r corresponds to the number of ways of arranging the non-selected items. And it divides out those duplications. All right, so that's basically how why the formula looks the way that it does. We're going to take a look at some examples of calculating with it next. Okay, so here a $1,500, $1,000, and $500 scholarship are to be awarded. That's 3 different awards. We want to know how many ways there are to select the 3 winners from 8 finalists. So here, of course, it matters what order those top 3 people are in. Winning $500 is different from winning $1,500 or $1,000, right? So it's going to be P and R. And here there are a total of 8 finalists. And we're choosing 3 to give a prize to, the scholarship. Okay, so that is going to be our n factorial on top, the number of ways of arranging all of the 8 finalists. And then we're going to divide by 8 minus 3 factorial. That's the number of ways of arranging the 5 people who don't get anything, right? So we have 8 factorial divided by 5 factorial. Okay, so you can do this on your calculator, or you can simplify a little bit. I'm going to rewrite the 8 factorial as 8 times 7 times 6 times 5 factorial. And the reason why I'm going to do that is just so that I can cancel out those two 5 factorials. And so we'll have 8 times 7 times 6. And that's like 336, I think. Yeah, 336. So there's 336 ways of making that assignment of the prizes. As I'd mentioned, there's a couple of different notations for this. I wrote P83. You may see 8P3, and it's going to mean the same thing. Okay. All right, so another example, more examples. We want to find P29. So you can use a calculator for that if you have a calculator that will do it. Otherwise, we're going to do it by hand. So that is going to be 20 factorial divided by 20 minus 9 factorial. I've repeated the formula up here for your reference. Your calculator, some of these factorials get really big. So you're going to run into some large numbers calculating these things, okay? So let me find out 20 factorial. Divided by 11 factorial. Okay, that's a really large number. Okay, so that's a really large number. Out of 20 things, pick 9, and the order they're in makes a difference. Okay, this is smaller. This is going to be a little more palatable. We want the number of permutations out of 5. Take 2. Okay, so that's 5 factorial over 3 factorial. This is small enough that I can just do this directly. So that's 5 times 4 times 3 times 2 factorial. We're dividing by, that's actually 3 factorial we needed to go to. All right, so this time again, the 3 factorials cancel, and this will leave us with just 20. So there's 20 ways of arranging those 2 items that are selected. Okay, more examples. Pn1, so that will be n factorial divided by n minus 1 factorial. All right, so this one, it's because it involves just n's here, not like specific values. You might have take a little more thinking to get this done, but we need to think about how to simplify the factorial expressions a little bit. And I had done one on our last page that involved this. Remember that like 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is, for example, 4, 3, 2, 1. So notice that 5 factorial is 5 times 4 factorial. And if you think about it, what would 6 factorial be like? 6 factorial would be 6, 5, 4, 3, 2, 1, or 6 times 5 factorial. In general, n factorial is n times n minus 1 factorial. So you can peel off one number and then multiply by the factorial of the preceding number. So n factorial in our example here, we'll write that as n times n minus 1 factorial. And down below, we still have n minus 1 factorial. Those two n minus 1 factorials are going to cancel out. And that will leave us just with n, right? And if you think about it, that makes sense. If you have n things, n people, right, and you're going to pick one of them, how many ways are there for you to pick the one person? Okay, there's n of them. Okay, you've got 8 friends, and you're going to pick one person to have come over for dinner. How many ways are there for you to pick one of those 8 people? There's 8 choices. Okay, so it makes total sense that we came out with n. Okay, so let's try the next one next. Out of n things, we're choosing n of them. How many ways are there for us to order that? So there's n factorial divided by n minus n factorial. we have n factorial in the top, and n minus n is 0, so we have 0 factorial. Be careful here because we're not dividing by 0, okay? Dividing by 0 is forbidden, of course, right? But remember that 0 factorial is equal to 1, right? 0 factorial is 1, so we have n factorial over 1, which is just n factorial. Okay, so let's check to see if this makes sense. If you have n total things and you're picking all n of them, how many ways are there for you to make that selection? Well, it's like having 8 people and you're lining up all 8 people for a photograph. Well, there's n factorial or 8 factorial in that case, number of ways of getting that done. In this next part, we're looking at kind of a variation on the permutations idea or the n factorial idea. And that's when we're counting arrangements of objects, but where some of the items are duplicated. So we talked about how if you had 4 phone calls to make, right, that it ended up being 4 factorial, the number of ways of arranging 4 objects. Or if I asked you, how many ways are there for you to respell the word boat? Okay, how many ways are there for you to rearrange those letters? Okay, there's 4 factorial ways to rearrange those letters. Okay, most of them won't make words, but in any case, there's 24 ways for us to rearrange those letters. What this part is about, the next 2 examples, is how many ways there are to rearrange something where some of the things are alike. Okay, so for example, here we saw that there were 4 factorial or 24 ways to arrange those letters. But what about the word apple? Okay, here, if I change the E and the L, that's going to form something that looks different. And so that would count as another permutation. But I can't really just say, okay, well, that would be 5 factorial. Why? Because let's say I swap the 2 P's. Okay, if you switch the 2 P's, it's not going to create something that looks different. And so we need to account for that. That's what this is about. So here's the formula. The number of different permutations, here order matters, when n items are available and all n are selected without replacement. But some of the items are identical is like this. You again divide n factorial, but you're going to divide by n1 factorial, n2 factorial. All these in the bottom are multiplied, okay? n1 factorial, n2 factorial, and so on, where the n1, n2, down to nk are the ones that are alike. Okay, so the best way to see how to work this formula is by example. Let's say that we've got the word kitten, which is a 6-letter word, and we want to figure out the number of ways to rearrange those letters. So it's 6 factorial on top, because there's 6 letters in kitten. And then down below, the ones that repeat are the T's, okay? And there are 2 of them. So we will have 2 factorial to account for the 2 T's. Okay, why are we dividing? Okay, because 6 factorial is 720, right? But there aren't 720 different ways to misspell kitten, right, that are going to look different, because each time you swap the 2 T's, that doesn't generate a different looking word. So that's why we end up dividing by 2, and that's just going to equal 360. So there's just 360 ways of making that happen. Okay, here's another example. Same story, different example. We want to find the number of ways of rearranging the letters in statistics. So how many letters are there altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. Let me count again. 4, 8, 10 letters. So there's 10 total letters. And then we need to think about which ones are duplicated. So I see several S's. There's 1, 2, 3 S's. If I trade those 3 S's, it's not going to look different, so we need to account for that. There are 1, 2, 3 T's. So let's account for that. And then it looks like there are 2 I's. 1, 2 I's. Okay, I want to make sure I didn't miss anything, so let me see what the others are, because there's 3, 6, 8. There's 2 other letters. That would have to be the C and the A. Okay, and there's only 1 each of those. Okay, so let's go ahead and figure that out. 10 factorial, just so you know, is 3, 6, 2, 8, 800. Okay, so a little over 3.5 million. So it sounds like a lot of ways to rearrange the 10 letters in a 10-letter word. However, as you can see here, there's some duplicatings. If I switch the T's or switch the S's, nothing happens. So we're going to divide our 3.5 million number by, that's 3 factorial is 6, times 6 is 36, times 2 is 72. So 50,400. Now we're dividing by 72 and getting 50,400. All right, so there's actually only around 50,500 different ways of respelling statistics. Okay, so this application can seem kind of minor, like how many days, how often do you sit and need to figure out how many ways of respelling a word. So that's kind of a minor application for this, but that's how that goes. All right, so let's move along. Okay, we want to look at combinations next. So we talked about permutations. Permutations are the number of ways of arranging R things taken out of a total of N things, and the order makes a difference. The difference with combinations is that the order of the selected items doesn't matter. So as before, we want to look at a formula, see where the formula comes from, and then try some examples. Okay, so fine print here. When N different items are available, but only R of them are selected without replacement, as always, the number of different combinations, that in, again, order doesn't matter, is found as follows. And there's a formula for this. Let me start kind of on the inside. CNR, okay, or NCR, where it was a P for permutations, now it's a C for combinations. CNR, the number of combinations of N things, taken R at a time, is N factorial divided by N minus R factorial. And then what's different on this formula is that in the denominator, there is an extra R factorial. And we'll talk about why that's there here in a few minutes. But the formula for permutations, as you saw, was just N factorial over N minus R factorial. This one looks a little different. It's got an additional R factorial in it. In fact, you may see the combinations formula written like this as the permutations formula, and then you divide by R factorial. And as I said, we're going to talk about why you do that here in a second. Okay, other notation you may see for this is the N stacked on top of the R and then wrapped in parentheses. This looks almost like a fraction, like 3/5 in parentheses, only it isn't, of course. There's no bar in between. Okay, so you might see 10 on top of a 7 with no like fraction bar because it's not a fraction, but that's the notation. Okay, instead of writing NCR or CNR, you might see this one number on top of another and then wrapped in parentheses, no fraction bar in between. This is the number of combinations, what I have written here, of 10 things taken 7 at a time. Okay, sometimes people will read this out loud as N choose R, because R things are being chosen out of N. Okay, so enough about that. Let's talk about why the formula looks the way that it does. We're going to go back to our letters A, B, C, D, and E again. So we talked about how the formula for permutations looked like N factorial, the number of ways of arranging all of our objects. In this case, for the letters A through E, it would be 5 factorial or 120. Okay, and then we talked about why we divide by, in this case, it would be 2 factorial. To eliminate the duplication caused by reordering the D and the E, right? Because we said, okay, if it's permutations, then I don't want to count these first 2 rows separately because it doesn't matter what order those last 2 are in. And that's why we had the N minus R factorial in the denominator. The thing is that now that we're considering combinations, we want to also take these 3, or these 2, A, B, C, D, E, and A, B, C, E, D. Those should be the same as these 2, right? Because A, B, C, and A, C, B are the same. So in addition to dividing by the duplication caused by reordering what's not selected, which was the n minus r, we are also dividing by the number of ways of arranging the selected items, which is the r factorial. So we take the total number of ways of arranging everything. That was n factorial. We divide by the n minus r factorial, which is the number of ways of arranging the non-selected items. Also, we divide by the number of ways of arranging the selected items. And that's why in here, if we're going to calculate C53, we'd also have a 3 factorial in here. So both, let me put this in the correct order, 3 factorial and 2 factorial. Okay, so that would give us 10. There's only 10 ways of choosing 3 letters from 5 if the order that they're in doesn't make any difference. Okay, so examples. Okay, let's say that you have 6 friends and you want to take 2 of them to Disneyland with you. Okay, let's say that you won 3 tickets on a radio station. Of course, you're going to go, right? And so you need to pick 2 of your friends to go with you to Disneyland out of the 6. And how many ways can you choose 2 to go and anger the others, right? So out of 6 people, you need to choose 2. So you also have to decide, does the order matter or not? Is it permutations or combinations? The 2 people who are going to Disneyland with you, they're going, right? The others are not. And so the order they're in doesn't make any difference. So it's C, I have 6 friends and we're choosing 2 to go. So there's 6 factorial in the top. We'll have 6 minus 2 factorial and then 2 factorial. 6 factorial in the top was 720. 6 minus 2 is 4. 4 factorial, and then the 2 factorial is a 2. We have 720 times 24 times 2. Okay, and that's 15. Okay, so again, this 6 minus 2 factorial, this is the ways to arrange the unselected people. Okay, your other 4 friends who are not going. And then we have the 2 factorial, which is the number of ways to arrange the selected people, the ones who are going. Okay, because the order that both the selected and unselected groups are in doesn't matter, which is why we divide out those duplications. Okay, another example, suppose that you belong to a club, it's got 10 members in it, and we're going to select 4 people to go to a regional meeting. So those 4 people are just going, okay, and it doesn't matter what order they are in. So it'll be 10C4. I'm using the other notation here just for variety's sake. That's the same as 10C4. Okay, same idea, different notation. Okay, so then we'll have our 10 factorial in the top. Then 10 minus 4 factorial and 4 factorial. Okay, so this will work out to be 210. Okay, if you have trouble making this come out on your calculator or something, let me know. And I can try to help you with that. So there's 210 ways of us selecting those club members. All right, so we have a couple of more examples here. So for this first one, we want to know how many possible triangles can be drawn using the dots shown in this picture. So thinking it through to draw a triangle, well, here's one of them. There's one. Here's another one. How many possible triangles would it take? So let's think about it. How many dots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 total dots. And then if we're going to draw a triangle, we need to pick 3 of those dots and connect the dots. So out of 9, we need to get 3 and connect the dots. So now the next question is, does it matter what order we choose the dots, or are they just chosen or not? So thinking about it, can you tell, do you remember, without rewinding, which order I drew, like the triangle, right? Did I draw ABC or CBA, or which dot was chosen first, right? It doesn't matter what order the dots were chosen in, right? So that makes it combinations. Okay, so then this will be n factorial divided by n minus r, so that's 9 minus 3 factorial, and then 3 factorial. Okay, so that's 84. There's 84 possible triangles that we can draw using those dots. All right, another example. Here we have a grid. The upper left corner is the point A, the lower right corner is the point B. Let's say that you can only go, you want to travel from A to B. Let's say that this is a city arranged in blocks, right? And we want to travel from A to B, and we can only go down, that is south, or right, which would be like east. We want to know how many paths there are from A to B. So what's possible? Well, we could just go to the left as far as possible and then down. That would be one choice. Or maybe we could go part way down and then across and then the rest of the way down. Or maybe you'd like to zigzag all the way there, but not quite. Okay, how many ways are there for us to do it if we can only go down and right? So we're not allowing us to do anything like, let's go around in a circle and then come down and up and down and back, or anything like that. We're not doing anything like that. So just down and right. So we need to think about that. How many ways are there for this to happen? So let's think first of all, how many blocks you have to travel. You have to go 1, 2, 3, 4 across, and 1, 2, 3, 4, 5 down. So we could think about trying to describe all those paths. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 blocks that you would need to travel. Some of them are down and some are right. The one where it's all across first and then down would be right 4 times and then down 5 times. That would be one recipe or path from A to B. We could alternate right, down, that's 2 R's, 3 R's, 4 R's, and the last 2 would be downs, 1, 2, 3, 4 R's. Okay, so this would give us yet another pathway to take to get from A to B. So if I were to write these down, write down more paths, I need to have 9 letters chosen, and 4 of them need to be R's, right? So out of the 9 places, we need to get 4 of them to make R's. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I'm going to write down another path from A to B. So I need to write down 4 R's, and the rest will be D's. So I could do that one, that one, that one, and let's go with that one. Okay, so out of the 9 total spots, I picked 4 to put an R. Okay, does the order we make those selections in matter? It doesn't, right? Do you remember which R I wrote first? Okay, if you don't remember, and it doesn't matter, right? It doesn't matter which R I wrote first. What matters is which one is chosen to be an R and which one isn't. So again, this will be combinations. Okay, so out of 9 total things, we're going to have 4. Okay, and so that will turn out to be 126. Okay, so there are 126 paths from A to B. All right, a couple more examples. Okay, let's say that you have 6 books that you've been meaning to read. You could take a nice long trip. So you're going to pick 4 books to take with you on this trip to read. How many ways are there for you to choose the 4 books? So we're not talking about the order that you read the books in. We're just, are they going to be in your suitcase or not, right? So how many ways are there for you to select those 4 books? So the order that the books are in doesn't matter, right? They've just gotten thrown in your suitcase. So it's combinations. Out of the 6 books, 4 need to be selected. Okay. Sometimes the hardest part on this is just deciding if it's combinations or if it's permutations. Okay, this is going to be 15 ways. Out of the 6 books, we're choosing 4 to take on a trip. Okay, a musician knows 6 songs. How many ways are there for the musician to choose 4 to perform? For this one, if you think about it, the order is going to make a difference, right? Maybe they don't want to finish with the sad song or something. They want to finish on something upbeat. Maybe they're trying to tell a story by telling or singing these songs in a certain order. So the order the songs are in makes a difference. So that'll be permutations. Out of 6 songs, 4 are chosen. So we'll have 6 factorial on 6 minus 4 factorial. Okay, do you think that there will be more? It's 6 and 4 again, between the book and the musician one. Do you think the number will be bigger or smaller? Okay, it should be bigger, right? It's 360. If you think about it, it should be bigger. There's more ways for something to happen if the order that it is in matters. Okay, so there's 360 ways for the musician to choose those 4 songs. Okay, so a couple of notes. You have to decide, does the order the selections are in make a difference? If so, it's permutations. If not, it's combinations. One thing that's important to note is that, and we touched on this a second ago, is that the number of combinations will always be less than the number of permutations. Because if you're not counting the order things are in, there's fewer ways that for that thing, whatever it is, to happen. Okay, and then also remember, the CNR and PNR are about selecting some out of a total to rearrange. N factorial is about arranging everything. Okay, CNR and PNR are about taking R things out of N total things instead of arranging all of something. Okay, we're getting there, almost finished for the day. Okay, so here's a probability problem. We're learning all this counting stuff to help us with probability, so we should do a probability. Okay, so here an applicant pool has 8 men and 6 women in it. So these 14 people have applied for a job and have made it through the paper screening process. 4 people are going to be picked for an interview. We want to know the probability. If it's random, if we want to know the probability that 3 are men and 1 is a woman. So probability is a fraction, right? The number of ways that something can occur goes in the bottom, and what we count as the success outcome, or the thing that we're interested in, goes in the numerator. So how many total possibilities? So there's a total of 14 people, and 4 people are selected for interview. So out of 14 people, let's say we just draw names out of a hat. Got to pick 4. So that's combinations. It's combinations, not permutations, because the order that the people are chosen for interview in doesn't make any difference. Okay, people are just either chosen or they're not chosen. Okay, that's the total number of ways that this can occur. So then for the numerator, we need to think about the number of ways of getting 3 men and 1 woman. So that's a big task. We're going to break it down into 2 subtasks: the number of ways of selecting the men and the number of ways of selecting the women. So out of the 8 men, 3 will be chosen for interview. Out of the 6 women, 1 will be chosen for interview. So that's a fundamental counting principle problem. This is kind of like picking shirts and pants again, right? So we're multiplying these 2 together. The number of ways of picking the men, 3 chosen out of 8, and the number of ways of picking the 1 woman out of 6. We'll multiply those 2 together because that's the probability that we're interested in. The number of probability or chance of us getting 3 men and 1 woman out of this pool of 8 men and 6 women. Okay, so let's calculate. 1001 in the bottom here. $56. The number of ways of picking the men was 56, and then it'll be 6 for the women, right? Or about 0.34. Okay, so a little over a 1/3 chance. Okay, so if you have a lot of these applicant pools with 14 people that have 8 men and 6 women, in the long run chance of us getting 3 men and 1 woman is about right around 1/3 of the time. Okay, what is the chance that we get all women? So the same denominator. Okay, and then for this one, out of the 6 women, 4 will be chosen, and out of the 8 men, none will be chosen. Our denominator is still 1001. Okay, then let me do the men first. Out of 8 men, we're choosing none. How can that happen? There's only one way that that can occur. I'll leave it to you to run the formula for that. But out of 8 men, we're choosing none. There's only one way for that to happen. Out of the 6 women, 4 are chosen. And so there's 15 ways that can occur. Okay, so about 0.0149. Okay. So here, about a 1.5% chance of getting all 4 women in that case. Okay. All right. So this has been our first example involving a probability where we've used a combination. So another example, this time it'll be permutations though. Let's say we have 8 horses running in a race. For the first part, we want to know how many ways are there for the first, second, and third horse to finish. So it's different to come in first versus coming in third, right? So out of the 8 horses, there will be 3 winners, right? And so permutations, how many ways are there for us to get 3 horses from 8, and the order matters. So there is 8 factorial on the top, number of ways of arranging all 8 horses, and then 8 minus 3, or 5 factorial in the bottom. We have 8 factorial, down below 5 factorial. That 5 factorial, again, represents the number of ways of arranging the 5 losing horses, because it doesn't matter what order they are in, right? What matters is the order of the top 3 horses. So we'll have 8 times 7 times 6 times 5 factorial. That's divided by 5 factorial. 5 factorials cancel, leaving us 8 times 7 times 6, which is 336. Okay. All right, so that's the number of ways that this race can finish. Okay. Now, to contrast that, we want to find the probability that you choose the top 3 correctly. So let's say we've got this list of 8 horses. We want to pick the 3 horses that will win. Who will be first? Which horse will be second? Which horse will be third? What is the probability that you make that selection correctly? So there, we've seen just now that there are 336 total possibilities, but only one of them is correct, right? So it's a 1 in 336 chance. And that's about 0.003. So you have about a 0.3% chance of guessing or figuring out that top 3 winning horses correctly. It's important to make sure that you know the difference between finding the number of ways something can occur, like this 336, versus the probability, which was the 1 out of 336. Make sure that you know a question is asking you for a count, a number of ways something can occur, or the probability that something can occur. All right, so this takes us to the end of this video. We're not quite done with section 4.4. We'll have more to do yet, but that's it for right now. Let me know if you have any questions, and have a great day.